All right, in section 6.2, we have properties of radicals. And so I wanted to look at a couple of problems that show up a lot. You may even remember some things from geometry. Let's look at number 9 first. We have the square root of 4 over 3. Now, when we have radicals and we have fractions underneath them, we can break apart and take, if it's a square root, we can take the square root of the top and the square root of the bottom. We can do that no matter what kind of root it is, actually. It could be a cube root, and we could do this. Okay? Well, now, what is the square root of 4 on top? It is 2. And again, the reason we don't put a plus or minus on it is they already had the root on it. I didn't square root it myself in solving. All right, but I have a square root of 3 on the bottom. Now, in math, it's considered impolite to leave that square root in the denominator. And so it's kind of just polite communication, like using proper grammar in English, for instance. So we want to get rid of that radical in the denominator. Well, I've got one square root of 3. How can I change that into a whole number? Well, if I had another square root of 3, that would do it, because that would be the square root of 3 times 3, and that would be the square root of 9, which is just 3, right? That's why we did that. But remember, in math, if you do something to the bottom of a fraction to keep the fraction equal, to have an equivalent fraction, we need to do the same thing to the top. So I'm going to multiply the top also by square root of 3. So I end up with 2 square roots of 3 over 3 is my answer there. 11 is a similar type problem. The only difference with 11 is that you didn't have to do as much work. It's a little less work than number 9. You look at it, it's got a square root in the denominator. It would be okay except for that, right? So in order to get rid of that, a square root means that you've got two of the same things, right, to make a whole number. So if I want a whole number instead of a radical in the denominator, I'll need another square root of 2. But if I multiply the denominator by square root of 2, I need to multiply the numerator by square root of 2. So I get 4 times square root of 2 on top is 4 square roots of 2. And then square root of 2 times square root of 2 on the bottom. Remember, that would be, you could put those together. I'll put a few more steps in here. You could put those together, and you could look at it as, oh, I have 4 square roots of 2 over, I've got 2 copies of something under a square root, so it's 2. Or you could also say, well, 2 times 2 is 4, and the square root of 4 is 2. Now, we're not through yet, because we can reduce this fraction a little bit more. You can only reduce with radicals. Whole numbers on the outside of radicals can be reduced together, and things inside of radicals can be reduced together, but you can't mix them. So I can't, like, for instance, cross out that 2 on the bottom and the 2 under the radical. But I can say, okay, here's a number outside of a radical. 2 goes into 2 once, and this 4 is outside the radical, so 2 goes into 4 2 times. So I end up with 2 square roots of 2 over 1, which is just 2 square roots of 2. Okay, on number 15, we see another property of radicals, and that's if we're multiplying two radicals together, and they're both square roots. They both have to be the same type of root, either both square roots or both cube roots or so on. And these are both square roots. So what I can do is I can combine the two numbers under one radical. And why I might want to do that, it might be easier to reduce it this way. Now, there's a couple of things I can do here. I could look for perfect squares hiding in these. I could even do this. I could, if I'm really stuck, I could prime factor each one of them and then look for pairs to pull out. Let me do that here. 30, let me come off to the side, is 3 times 10, but 10 is 2 times 5. So with the 30, I have, let me put them in order, a 2 and a 3 and a 5. Now 42, I know is like 6 times 7, right? But 6 is 2 times 3. So I could also then replace 42. Let me put, here was 30 in one parenthesis. In another parenthesis, I'll put the factors of 42, and I'll put them in order, least to greatest, 2 times 3 times 7. Now, if you're thinking about now the whole, I need 2 copies of something to get it out of a square root. The whole square root dance analogy I may have used with you when you were younger. I have 2 copies of 2, so a 2 comes on out the outside. In other words, 2 times 2 is 4, and the square root of 4 is 2. Okay? Now I have 2 3's here. I have 3 times 3. Well, 3 times 3 is 9, and the square root of 9 is 3. Or you could have just said I have 2 copies of 3, so there's going to be a 3 that comes out. They were multiplied under the radical. When you bring them outside of the radical, they're also multiplied. Now, I've got some stuff left inside that didn't have a partner to get out or didn't have another copy. I have 5 times 7. So what I want to do is put those back together. Since they can't get out, 5 times 7 is 35. So I would want to write my answer this way. 2 times 3 is 6 on the outside, and then it would be 6 square roots of 35. I wanted to do one with the cube root. We work with square roots a lot, but you also have cube roots you can worry about. All right, now look at what we've got here. Let me go ahead and split this up. We got the cube root of 5 over the cube root of 4. We could write it either way. Those are equivalent. We can break them apart that way. Now, in this case, what's wrong is that I still have a radical in the denominator, and that's a big no-no. So I want to get rid of it. And in this case, I'm dealing with a cube root. So with the cube root, I can't just multiply by one more copy of 4, because if I put another cube root of 4, that still won't get it out of the radical, because that's just 2 copies of 4, and a cube root, I need 3 copies of 4 to get it out of the radical, so I need another cube root of 4, and then that would be 3 copies of 4 under a cube root would give me a 4 on the outside. I could say 4 times 4 is 16, times 4 is 64, and the cube root of 64 is 4, but that's kind of almost unnecessary multiplying that I would do there. If I just see that I have 3 copies, that brings the 4 out. Now, if I do something to the bottom of a fraction to keep it equivalent, I need to also do it to the top. So I got to do a cube root up on the numerator on each one of these that I added. So now what do I have? I have the cube root of 5, and they're all cube roots, so I can put them under one radical. 5 times 4 times 4. Now that numerator is not going to simplify anymore because you don't have 3 of a kind of anything to get it out. So what we do in that case is we go ahead and we multiply this stuff inside the radical, which we're going to have a 4 on the bottom, but to clean up the top part, 5 times 4 is 20, times 4 is 80. The cube root, there is something we can do. Let me backtrack a little bit. These were not prime numbers, were they? Because they were not prime numbers, in order to be sure that there's not something hiding in there that could, come out, and there was something, I could prime factor them. So that would be 5 times, now 4 is 2 times 2, then I have another 4, and that's 2 times 2. Do you see what we can pull out now? There were 3 copies of 2. So what I can do is bring a 2 out now, because there's 3 copies of 2 under a cube root. Or in other words, 2 times 2 times 2 is 8. The cube root of 8 is 2. Or you're going to a cube root dance. You need 3 of a kind to get to go out as one group. And we got one group of 2 under there. Okay. Now I've got the cube root of 5 times 2 left on the inside. And on the bottom I have a 4. Okay, there's still a couple of things I need to do to clean up here. On the outside, the whole numbers that are not under radical, they reduce. 2 goes into 2 once and 2 goes into 4 twice. So that's one thing I can do. I'll have a 2 in the denominator. I don't really need that 1 out front, so I'm not going to write it. Now, inside, I can't pull any more factors out. Those are prime on the inside. I can see there's not 3 of a kind of anything. So 5 times 2 is going to be 10. So we have the cube root of 10 over 2, and that would be our answer for 21. It must look like that or it's not correct. 25 is not hard. I just want to do one like this just to make a point, just because there's all kinds of different types of things that can happen here, and I want to make sure that we've looked at all the things that can happen. If I have something, I square it, that means everything inside the radical gets squared. For instance, this whole thing is squared because it's in these parentheses right here. So I got to square the part outside the radical and the part inside the radical. So what this is equivalent to is saying 2 squared times square root of 7 squared. Well, what's 2 squared? It's 4. What's the square root of 7 squared? I have 2 copies of a square root, so that means it's just 7. Or you could think of it this way. 7 times 7 is 49, and the square root of 49 is 7. So this is just 4 times 7 is 28. Okay, let's look at number 29. I've got the cube root of 60 over the cube root of 36. Now, there's a lot of different ways we could approach this. Here's what I'm going to do. They wrote them separately. Let me write it together. This is 60 over 36. Now, what I'm going to do is just reduce the fraction first. we can reduce that fraction without having to go do all this prime factorization that would take us some time. For instance, I know that 6 goes into 60 and 6 goes into 36. There may be something bigger, but let's just start there. That 6 goes into 60 10 times and 6 goes into 36 6 times. Now this is still all under the radical. I'm just reducing, so let me just draw that little radical a little longer so you see that. But that's still not reduced all the way because both of those numbers are divisible by 2. So 2 goes into 6 3 times and 2 goes into 10 5 times. So what I really have here is the cube root of 5/3. And that's reduced all the way. And so that's the fastest way to take care of that, is just to reduce the fraction first. Now, what I'm going to do to simplify this is let me go ahead and split it up into 2 parts. That's the cube root of 5 over the cube root of 3. And what's wrong with that? It's got a radical in the denominator, so we know we got to clean that up. And this is a cube root. So in order to clean it up, I need 2 more copies because I need a total of 3 copies of the cube root of 3 in order to get just a 3 on the bottom, and that's what I want to do. So I need 2 more copies of the cube root of 3. Now on the top, if I do something to the bottom of a fraction to keep it equal or equivalent, I need to do it to the top. So I need another cube root of 3 on the top here and a cube root of 3 on the top here. So that's the cube root of 5 times 3 times 3. Do you see how we're always pulling these things apart and putting them back together? You know, if you can't do something with it one way, put it back together. You know, if you're working on it and you're not getting anywhere, try doing the opposite thing of what you're doing to see if you can figure out something to do. Okay, so there's no cube roots on the numerator. So what I'm going to do, since there's no cube roots left, those are all prime factors, and I know there's nothing that's going to come out, is I'm going to go ahead and multiply those together. 5 times 3 is 15, times another 3 is 45, so that's the cube root of 45 over 3.